Hi everyone, this is Mr. Bowman, and in this video we are going to focus on Riemann sums, the intermediate value theorem, the extreme value theorem, and the mean value theorem. In this problem we are allowed to use a graphing calculator and we're given information in a tabular form. Let's see what we have. A tank has a height of 10 feet. The area of the horizontal cross section of the tank at height h feet is given by function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table above. Use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measure. Okay, so a left Riemann sum means that we're going to make rectangles based on the height of the function's left-hand side. So we're also told 3 subintervals. So our subintervals are going to go from 0 to 2, 2 to 5, and 5 to 10. The heights that we are going to use are the left-hand side of the intervals, the height of the function or the value of the function at that time. So what we're going to do is we're going to take the width of the interval times the corresponding height. So 2 times 50.3, 3 times 14.4, and 5 times 6.5. The volume of the tank would be equal to the integral from 0 to 10 a of h dh. Okay, integrate the area of the cross section of the area over the interval that we have. So that is approximated by that Riemann sum. So the value of the function at the left-hand side, 50.3 times 2, plus the value of the function at the left-hand side, 14.4, times the width of the interval, 3, plus the value of the function, 6.5, times at the left-hand side, times the width of the integral of 5. And you can use your calculator for that, and that would turn out to be 176.3 feet cubed, okay, because we're integrating square feet over dh is going to be in feet. Indicate the units of measure, so make sure you include that as well. So let's take a look at the scoring for this. The scoring for this, notice it says you get 1 unit, 1 point for units in parts A, C, and D. So it looks like you got to do units in all of those to get that 1 point. 1 point for the left Riemann sum, 1 point for the approximation. So I don't know what they mean by the approximation. I don't know if they mean the actual value that you get, but here's the Riemann sum, and here's the Riemann sum, and here's the integral that we'd have to find. In part B, does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Alright, so Riemann sums, whether or not they overestimate or underestimate, is based on whether or not the function that we are integrating is increasing or decreasing. And we are told that function a is continuous and decreases as h increases. So if you imagine a decreasing function, okay, so here's a of h, and here's h, and here's this decreasing function, and we are using left Riemann sums, okay, so left Riemann sums to estimate the area under the curve, between the curve and the x-axis over that interval. You can see the area of the rectangles total up to more than the area of the curve. So the answer would be an overestimate because a of h is decreasing on the interval from 0 to 10. Now, whether or not you have to state that on the interval, I doubt, but let's check and see. Only 1 point. Overestimate with a reason. So if you say overestimate or underestimate without a reason, you're not going to get the point for that. So let's take a look at letter C. The area in square feet of the horizontal cross-section at height h feet is modeled by the function f, given by f of h. Based on this model, find the volume of the tank, indicate units of measure. So I found this a little bit confusing because earlier they told you the horizontal cross-section is given by A of h. Basically they're saying, oh, now it's changed. So we're going to do the same thing in C that we did in A, except we get to use a calculator to find this integral. So for C, we are going to find volume by integrating the area of the cross-section from 0 to 10, which is f of h dh, and using your calculator, that turns out to be approximately 101.325 feet cubed. Okay, remember we needed to have units on parts A, C, and I believe it was D. So we've got our units, and essentially we've got 2 points, one for the integral, one for the answer. You can't just put an answer down without showing your work, even though you're allowed to use a calculator. And as can be expected in part D of this question, not just part D's, but in these questions in general, they throw what I would consider kind of a curveball at you. So let's take a look at this question. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot per minute. Using the model from part C, find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet. Indicate units of measure. Okay, so our model from part C tells us that volume is a function of height. So V is equal to the integral from, in that we did 0 to 10 of f of h dh. What we're going to do is we're going to do 0 to h of f of x dx. We're using a dummy variable here because the volume depends on the height here. So essentially what we're saying is volume is a function of height and height is a function of time, and we want to find the rate at which the volume of water is changing with respect to time at a certain time. So we're basically saying let's find the derivative of v of h of t, which is v prime at h of t times h prime of t. And using a different notation, we're basically saying let's find dv dh times dh dt. Okay, so dv dh is equal to dh of the integral from 0 to h of f of x dx, and by the fundamental theorem that turns out to be f of h. And dh dt, if you prefer, we can write it as h prime of t. So basically we need to take f and evaluate it at a certain height, and that height that we were given in the problem was 5, and then we need to take h prime and evaluate it at a certain time, and that time that we were given, well, let me correct that statement. We were not given a particular time. What we were told is that at the time the height was 5 feet, h prime of t is 0.26 feet per minute. So we're going to take f of 5 times 0.26 feet per minute. All right, so using the calculator, we are going to evaluate f of 5, and basically we're plugging that in. So we end up, when we simplify all this, with 1.694 cubic feet per minute. and we're simply plugging in 5 into function f, which they gave us right up here. And that should be our final answer. So let's take a look at the scoring on that. Alright, so using this model, dV dt, the rate of change of volume with respect to time at a height of 5, dV dH times dH dt at h equal 5. So we're going to evaluate f at 5, and we're going to multiply it times the given rate of change of the height when the height is 5. And we've got this number right here, and we should have units of cubic feet per minute. So 2 points for dV dt, probably because it's 2 parts, chain rule sort of thing, and 1 point for the answer, and then also 1 point overall for units on that problem. And that is it for that problem.